Welcome folks, in today's lesson we're going to talk about sound, speed and frequency, and maybe you're already familiar with the image on the left. You see it in many Hollywood films, Western films, where somebody puts their ear to a railway or a train track. And we're going to talk about why they might do that, whether it would be effective in any way, whether the temperature outside would make a difference. And of course they're hopefully trying to listen for oncoming trains. So we're going to learn about speed and frequency in today's lesson. So the first thing that we should talk about is we should maybe just go back to thinking about sound. And sound is a pressure wave, a longitudinal wave. And I covered that in a previous video of mine. So if you don't know what it is, you might want to check out the basics on waves. And the first thing we're going to talk about is the speed of sound depends on the medium it's traveling through. Now the medium is the material that the sound is traveling through. So if we look at the GIF at the bottom right, I think it does an excellent job in terms of showing that and modeling that. And it is using dominoes to show if those dominoes were closer together, they would be knocked much faster. And those dominoes are modeling molecules in effect. And in a solid, the molecules are much closer together. So the sound is going to move quickest through a solid, then a liquid, and then a gas. And the speed of sound in water is typically 1500 meters per second. So that's quite fast, obviously not as fast as light. The speed of sound in air is actually much slower, and that is around 343 meters per second, and there are various factors which can affect that as well, but approximately 343 meters per second. So, sound travels faster in warmer air. This is the second thing that we're going to talk about. So, two things which will affect the speed of sound. One is the medium that the sound is traveling through, and the second thing is the temperature of that medium. So, medium type and medium temperature. And the reason for that is that when we've got warmer air or a higher temperature, remember temperature is a measure of the kinetic energy of the particles, the molecules, and how quickly they're moving. And so warmer air means that the molecules have a much higher energy to begin with. And so those disturbances, that sound energy wave can be transferred, can be carried, if you like, through that medium much faster on a hotter day than a colder day. And the relationship is pretty much a linear relationship. This is a graph from the engineering toolbox, and you can see that it's quite linear. At temperatures approaching 80, 100, it starts to lose a little bit of that, but this is the speed of sound in dry air. And the linear relationship itself can be modeled by the equation on the bottom right. So the velocity is equal to 332 meters per second plus 0.6 times the temperature. Now you will see some equations which say 331.4, 331. Basically it's in between 331 and 332, but it can be approximated as I've put it on screen. So an example of a problem that you might see or that you might have to contend with, you see a flash of lightning from a storm 1.4 kilometers away and hear the crack of lightning 4 seconds later. Now, of course, what is the temperature of the air? Of course, we're going to see the flash of lightning instantaneously because the speed of a light is so much quicker, 3 by 10 to the 8 meters per second. But it's going to take a while for that crack of lightning to hit us. And we're basing it off that 4 seconds. So the first thing that we want to do is we're going to find the speed of sound in air. And we're just going to use our standard equation for speed, which is distance over time. We're going to plug in those values and we would get 350 meters per second. So this is the speed of that sound wave. Now you'll notice that it's not 343, and that's because of various factors. And one of the factors we talked about is the temperature. And you were asked to get the temperature, so maybe we need to just go about doing that. So now that we have our velocity and temperature equation, we can isolate for temperature. And when we do that, we'll see that velocity minus 332 over 0.6 will give us 30 degrees Celsius. And that gives us a nice way of finding that temperature value. So what about frequency and speed? Well, the frequency of any sound wave is always the frequency of the source. And it does not change or affect the speed of the wave as it propagates. And the speed of the wave is dependent entirely on the medium. So the type of medium and the temperature of the medium. And it is not dependent on the frequency. So in this visual, the tuning fork is set to a certain frequency. It might be 440 hertz or whatever. And it will vibrate, that amount of times per second. What about frequency, speed, and wavelength? Well, these three factors can be combined in a pretty nice wave equation that forms the basis of introduction to waves, and we'll get to that soon. Let's just go back and talk about what some of these things are. So a wavelength is a distance measurement, and that is the distance between two crests or two troughs as shown in the diagram in green. So it's the difference between a repeating pattern and a wave. And of course this wave would be moving, but we've just taken a snapshot of it on screen. And that distance is dependent on what type of wave it is. Now the period is the time taken for that repeating pattern of the wave. So for any cycle to occur, it is the time for that cycle. And so the wavelength is a distance and the period is a time measurement. So when we want to figure out what velocity is, we said it was distance over time. So we can use that and we can say that d is equal to lambda, so the distance is equal to the wavelength. And if we set our distance equal to the wavelength, then the amount of time that it takes that to happen is the period, because that's the amount of time it takes for one cycle to happen. And so we can substitute that in and we would get v is equal to lambda over big T. From a previous video we talked about how period and frequency are reciprocals of one another, and if you use that logic, then you can also rewrite it as v is equal to f lambda, or v is equal to lambda over f. And this is what's referred to as the wave equation, and it joins frequency, speed and wavelength, and it relates them. So what about us? Because we like talking about us. Well, us humans, we can hear in the range from about 20 hertz to 20,000 hertz, and the amount of frequency that we can hear is also dependent on our age. As we get older, that band narrows and shrivels and we can hear less and less. There are amazing creatures, cats and elephants and so on, that can hear at infrasound range. So this is from 0 hertz to about 16 hertz. And elephants, it's believed, use their trunk to pick up those infrasound sounds to hear what's close by and so on. There are creatures that use that, but they use this, but they do it at a higher frequency area. Are bats and dolphins. They use ultrasonic waves to navigate, and these are at frequencies above 20,000 hertz. So a practice question I'm just going to leave you with is on the screen. Bats produce ultrasounds of approximately 30,000 hertz. If the time for the echo to return from a moth is 4.6 by 10 to the negative 2 seconds, how many wavelengths are there between the bat and the moth? And you're given a speed that you can assume. So hopefully you found this introduction to speed, frequency and sound waves useful. And if you found it useful, if you could just give us a wee thumbs up, please.